Hello everybody. In this lecture we will be solving 1997 IMO problem number 1. Here is a view of this problem. In the plane, the points with integer coordinates are the vertices of unit squares, and the squares are colored alternately black and white. As you can see, I demonstrated a few examples here. For any pair of positive integers m and n, consider a right-angled triangle whose vertices have integer coordinates, meaning that the vertices are at the corners of the square somewhere. And the legs of this right triangle will have length m and n, and they will lie along edges of the squares. That's awesome. Let S sub 1 be the total area of the black part. I wish they called it S sub B, right? So showing the area of the black part, but that's fine. And S sub 2, S sub W, if you will, be the total area of the white part. And we define this function here, which basically tells you the difference between the black and the white areas in that triangle, the absolute value of the difference. So in the sense, how close the coloring is, right? So if the coloring is equal in terms of the area, if half of the triangle is colored white and half of it is black, then this difference would naturally become 0. Okay, the first part of the problem. We need to calculate the value of this function for all positive integers m and n, which are either both even or both odd. So the same parity for m and n. So what I did is, here I have two examples. I believe the first one, this one is a 6 by 6, and this one is a 4 by 4. So what I have in mind is to come up with a triangle here. Let's just try to make sense of the problem, right? So we have a right triangle like this, and I am curious in the case of 6 by 6, which is a special case of the legs. So 6 here and then 6 here. Well, how many white squares? So let's assume that the squares are obviously area 1, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9 whites. And then how many blacks? The blacks are a bit more crazy. 1, 2, 3, 4, 5, 6. Then these two would be 7, 8, 9. 9 black. Well, I wonder what would happen if, this one is not 4 by 4, this one is 6 by 4. So this dimension here is a 6, this dimension here is a 4. So again, I'm drawing, oops, I should be careful. So let's assume that the vertices of my triangle are here. So it would go through this point, maybe the midpoint here and the midpoint here. Yeah. So what happens now? Okay, so let's count the white parts again. So yeah, now the count is no longer easy, right? So I need to come up with a better strategy here, because you see these portions here, or these ones, they are not split in a nice way, huh? So that's troublesome. One thing I can see is, well, yeah, why not? This, because of the symmetry, it looks like this portion here have the same area with this portion. In a similar way, this portion here have the same area with this portion here, right? So therefore, so what it looks like is that the sum of, I need the sum of, let me use a different color, maybe green. So I need the sum of this, that one, and that one. But luckily, these two portions, this one and this one, are the same as these two. So therefore, I have 1, 2, 3, 4, and then 5, 6. 6 whites, and number of blacks, 1, 2. The same thing, huh? For instance, this area here would be the same as this one. This one would match with this guy, and that's it. So therefore, again, let's count again. 1, 2, this one is full, 3, 4, and then I have these two would add 5 and 6. 6 black. So the scoring that we have here, the scoring function f, looks like it's equal to 0 here, it's equal to 0 here. So would that mean that whenever m and n are both even, so it gives me kind of a strong intuition feeling that I should expect a 0. But why is that? Why would the area of the blacks be equal to the area of the whites when I have an even by even configuration? Well, I think the answer is hidden in the drawings that I had, right? So I think it's hidden in the symmetry. And to exploit symmetry even further, you can make the following, right? So I can come up with the following idea. It just turns out that this whole rectangle, right, is a 6 by 6 rectangle. All I did was to split it, divide it into two, and I'm just trying to calculate the area of the white and black in half of the rectangle. So it would be obviously due to the pure symmetry, right? For instance, if I take my my triangle here and rotate it 180 degrees, it will perfectly match with this triangle on the upper left corner, right? As a result, all I need to do is to count the number of white squares, count the number of black squares in the big rectangle, look at the difference, divide by 2. Does that make sense? Count the whites, divide by 2, minus count the blacks, divide by 2 is the same thing as count the whites minus count the blacks, divide by 2. But wait, whenever we have an even by even, the whole dimension, so even times even is even, we have an even number of squares, thanks to the symmetry. There is an equal number of white and black squares. As a result, when I divide those numbers by 2, still the difference is 0. And sorry, when I take the difference, the difference is 0. Then divide by 2, still the difference is 0. Does that make sense? So therefore, so the answer for part A, in the case of m n even, the function f will return the value 0, right? And proof, we can say probably complete the triangle into a rectangle, and thanks to the dimensions of the rectangle being even by even, there exists an equal let's call the area of the black and white squares in the whole rectangle as T1 and T2. Then we can say that T1 is equal to T2 inside that rectangle, implying that S1 of T1 over 2, which is just S1, right? Implying that T1 over 2 is equal to T2 over 2, which implies that S1 is equal to S2, further implying f of mn, which is equal to the difference between S1 and S2 is simply equal to 0, proving the first. Oh, not yet, not yet. This is the first case. Now we have another case. What if m and n are both odd? Now I have two more pictures for that. Yes, I'm prepared, right? So here, well, let's start with, doesn't matter, one of them. Actually, this one is more generic, so I don't want to waste my time on this. So let's just delete this one. Delete. Okay, so let's just focus on this picture. So what are the dimensions of this? 1, 2, 3, 4, 5, 6, 7. So this is a 7 by 5. So this is definitely an odd by odd in any randomly selected, let's say, picture grid. And these are the vertices of my right triangle. I think it will go through the midpoint here. So this is quite asymmetrical. Like that, I guess. So let's assume that the lower right region is where my rectangle is. Okay, I really messed up my picture pretty badly. So this in no ways go through the vertices, so you know how to do it. Okay, so now how do we do the count? So here why don't we just say that we use the same analogy that I started with? For instance, I just realized that this white area here, due to symmetry, is the same as this white area here, and then this white area here is the same as this guy here. And finally, I guess everybody here watching these videos would know that this area is half of this square, right? So therefore, if I had to count the total of the whites, I would have whites is equal to 1, 2, 3, 4, 5, 6. I will add these two to here and here. So therefore 6, 7, 8 and a half. So I have 8 and a half whites. And now let's count the blacks carefully. Okay, so I have my color. Yes, so let's invoke symmetry again. So this area here is equal to this area here. So this would, okay. And this area here is the same as this guy here. That makes sense. And this tiny bit is the same as this tiny bit. Okay. Okay. So for the blacks we have 1, 2, 3, 4. Right, so this one and this one, they add up to 1. So far we have 5, these two together. And then this guy and this guy we have 6. 7, 8, 9. Huh. That's strange now. This is a 9, not an 8.5. So how to approach this problem? Well, I guess the same way we did here, right? So this shape is it perfectly symmetric? Yes, it is. So what I mean by perfect symmetric is if I take this lower right triangle and I make a 180-degree rotation across this midpoint here, central point, I would get this top left corner and exactly the same coloring scheme. So therefore, what we would have then is whatever is the number of black squares in the big rectangle, we can divide it by 2. Number of white squares in the big rectangle divided by 2. Take the difference. That's S1 minus S2. Deal? Deal. Okay, so therefore, f of mn is simply equal to, yes, S1 minus S2, or 1/2 T1 minus T2 if we use the same notation. Now what is curious in this one is the following. So because it's odd by odd dimensions of our triangle, in fact, because you see the corners are all black, it turns out there is, I believe, one more black square than we do have white squares. For instance, if I count the black squares here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 black total versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 only white. That explains the half difference, right? So therefore, we have 1/2 times T1. T1 is the number of black squares in the rectangle, which is 18, minus T2, which is white one, 17. Aha! The 1/2 again, and that's it. So therefore, does that make sense? So therefore, we can confidently say that whenever we have an odd by odd dimension triangle, we complete it into the rectangle, there will be either one black or one white extra, right? And in that case, that will cause the discrepancy in the count. And when we divide by 2, because we are counting the whole rectangle, we divide by 2, we get the actual count of the triangle. We will get half. And it doesn't matter how you color it. Like if you have black in all 4 corners of the rectangle versus all white, wouldn't change the thing. So therefore, whenever m and n are both odd, this would imply, using the same type of notation, f m n is equal to 1/2, and the proof exercise for you, right? So you can just write down what we discussed together. Okay, so we are just done with the first part of the problem. Now the second part. Prove that f of mn is equal to 1/2 the max of mn for all mn. Now, the general case. So for all mn, what happens? Okay, so for this one, we have already studied what happens if m and n have the same parity, and we get 0 or 1/2 depending on if both are even or both are odd, and we completed this part on part A. There's nothing more to prove. So therefore now let's have a look at the remaining case where either m is even, n is odd, or m is odd, n is even. So without loss of generality, let's first look at what happens if m, the horizontal leg of the right triangle, is even, and n, the vertical leg, is odd. So I have a new picture here. So we are solving part B. M, so this dimension here, m, is even, and n, the vertical one, is odd. And in this particular example, I have m is equal to 4, n is equal to 5, but without loss of generality, we will be able to generalize it pretty quickly. So m is even, n is odd. We need to investigate this situation now. So our triangle will have the following corners. Again, lower right corner, and probably it goes through this point here. I wish I can draw a straight line. I think I can. So, and then we do have also this and this side as well, and we need to figure out the sum of the areas here. Now this one is problematic for sure because we cannot complete it anymore. For instance, this little piece, which is just our whole 1 minus this little area, well, I know this piece is equal to that, but I'm not trying to count the total, right? So I'm trying to count sum of the white ones and the sum of the black ones separately. So that's problematic for sure. So I need to find a convincing argument, right? A convincing way of adding these areas somehow, and then finding the value of f of mn. How to approach this problem now? Now notice again that the problem is not asking for an accurate answer, but rather an upper bound for the value f of mn, right? So therefore, if you might maybe pause the video here for a few minutes and try it on your own, but here is how to approach the problem, and that's fairly standard. So consider instead this red triangle with the following 3 vertices. This is a right triangle, and it is even by even dimensions. So when you look at this red triangle, because it's even by even dimensions, we have already obtained the case even by even here, that the function, the difference between the black and the white areas is 0. So therefore, inside this red triangle, the black-white difference is 0. So therefore, all I can focus is, yeah, let's just label these. So A, B, C, let's think of this point as D. So this point here is E. So what I claim is the following. So we can calculate f of mn for triangle ABC. That's our goal, right? So for our triangle ABC as the following. I can split it as the f of mn for triangle ABE plus f of mn for triangle, this is a very loose language now, I understand that, AEC. But then this term vanishes when m is even and n is odd, because n minus 1, so we are reducing the dimension of n by just 1. So now we have this new ABE, triangle ABE, whose dimensions are even by even, and the areas are equal. So the difference of the black and white areas is 0 here. Now we are left with the area AEC. Therefore, the difference of the black and white areas in triangle AEC would be the same as the difference of the black and white areas in the whole thing in the triangle ABC. However, now we are pretty lucky now, because this number for this triangle AEC in triangle, oops, that's triangle AEC, we have that f of mn is simply equal to, employing our formula, the difference formula, this the measurement of S1 minus S2 obviously cannot be greater than or equal to, right, the area of the whole thing, right? So the area of the triangle AEC. But the area of the triangle AEC is simply 1, the base, times the height is m over 2, which is, oh my goodness, oops, m over 2. And that's exactly what we needed. The 1/2 m, which is, so we have something going on here. That's pretty decent. So therefore it cannot exceed m over 2. Now let's also whenever the other alternative case, if m is odd, n is even. If m is odd, n is even. Analogously, you can figure out that f of mn would in fact be less than or equal to n over 2. So combining these two results now, this result and this result together would imply therefore that when the parities are not the same, f of mn will definitely be less than or equal to 1/2 the maximum of mn. That concludes the second part, part B of this problem. Finally, last part of the problem, show that there is no constant c such that f of mn is strictly less than c for all mn. Now, this case you might think, hey, we have already proved part B, where we have shown clearly that our function f is always less than or equal to 1/2 m and 1/2 n, the max of these two, whichever one is larger. Then one might consider, hey, is it possible to find a c for which our function is always less than c? It turns out this is not possible. So therefore these variables will be kind of binding. So, well, what I'm saying is we won't be able to find an upper bound for the values of f of mn. And for that, let's focus on the example we did for part B again. So let me just copy this shape, I guess. That would be an easy way to do it. And then home paste. I hope it will work. There you go. So we have this shape. We are considering part C. So we have the general case. Let's try to see if we can make sense of things. So let me actually expand this shape. I need more space. Well, this looks like a specific case, but you can easily generalize this case for any values. So let's assume that this is an m by, let's say that n, I pick n special, a special case. So if this case doesn't work, obviously the general statement would definitely be wrong. So I'm finding a counterexample in a sense. And let's consider n is equal to m plus 1. So the dimensions of our thing is m by m plus 1. And I have my triangle. Again, these are the vertices of my triangle, namely this one, and this one. So these are the legs of my right triangle. So these two are easy to draw. And finally, I have, not history, this one. I have the vertices. Come on. Yeah. Oh, no, not that way. Come on, help me. Okay, and then I need to fix this part too. Okay, come on. It's not helping. Okay, good. All right, so this is the area. So what I will do is, I'm gonna do it. So I'm gonna count the areas, right? So what we decided in the previous exercise. So if this is our triangle ABC, that's point E. If I had to complete it into a rectangle, I think we decided to call this point E. Let me go ahead and call this point here as K. And look what curious thing I will do. So we decided in the argument, in the previous argument, that the function, the value of the function fmn is simply equal to, for the triangle ABC, is the same as the value of the function fmn for ABE, which is just 0, plus AEC, right? ACE, triangle ACE. We agreed for that. Now I will actually measure this value f of mn for triangle ACE. But the way I will do it is I will separately count the S sub 1, and so the area of the black region and the area of the white region in triangle ACE carefully. Now notice that before I begin this thing, let's quickly check something. So we have this black area inside triangle ACE. Does everyone agree that this black area is similar to, so what I'm saying is triangle CKE is similar to triangle CAB. That's clear. Now what's also very interesting is that, hey, look at this. How about this triangle? This triangle is also similar to the big triangle, and this one as well, and this one too, and so on, right? So we are in the general case, M case, So therefore, you have a bunch of similar triangles. In fact, you have a center of dilation where we continuously dilate these triangles, right? So this is the center of our dilation, and so we have a bunch of similar triangles. How many of them? We have m of them, m plus 1 minus 1, which is m. We have m of them, m similar triangles, and their similarity ratios. Right, so we have m similar, let's write that down, black triangles, and so I need to somehow find the ratio of these triangles with respect to each other, right? If you apply the similarity ratios carefully, and what you can easily observe is that the similarity ratios between, let's say, this one, KEC, this triangle, and this one is in the ratio of, if you call this one as 1, this one comes out as m minus 1 over m, and actually the next one will come out as m minus 2 over m, and so on. The last one will come out as 1 over m. So therefore the similarity ratios between similarity ratios between triangle CKE and the other m minus 1 black triangles are m minus 1 over m up to 1 over m. Before I finish, let's calculate the lengths of these legs. So this one is obviously 1, and this one, if you calculate it carefully, it would be m over m plus 1 because of the dimensions. That makes sense, because this one is m plus 1, this one is m, so that gives you the dimensions of this one, obviously. So therefore now we are ready. Let's add the area of these black little pieces. So the black area of triangle black area of triangle AEC is simply equal to, well, we can say that if we think of triangle KEC, the area of KEC times, okay, so we have to write it based on the dimensions, right? So the similarity ratio are here, but when we square them, right, for the areas, so I would have 1 over m squared for the little one here, plus 2 over m squared, and so on, all the way to m minus 1 over m squared, plus m over m squared, right? M over m squared. That's it. And now this is standard, right? So we have a sum of squares. So we have the area of KEC. Well, we already calculated the dimensions of KEC. M over m plus 1 times 1 over 2. So m over 2m plus 1. So this one is easy. M over 2m plus 1. And then I can factor out the m square. 1 over m square is factored out. All we are left is this sum here. And finally, the square here and the m will cancel out. So we have 1 over 2m times m plus 1. And the sum of the squares here, we have a formula, which is m times m plus 1 times, was it 2m plus 1? Yeah, I think it's 2m plus 1 over 6. 6m, I would like to say. Let me over just over just 6 over 6. Yes, that was the formula. Right. Okay, so the m's would cancel out, m plus 1's will cancel out, and what we are left here is 2m plus 1 over 12. Now we can, in a similar fashion, calculate the area of the white part. Or no, I can be smarter than that. Okay, let's write that. So the area, the white area of triangle AEC, of this triangle, is simply equal to the whole area AEC minus the black area of triangle AEC. Now the whole of AEC is just m over 2, right? So the dimensions are m by 1, m times 1 over 2, right? M is the height, minus this number here, 2m plus 1 over 12. So when we do the algebra, we would get 4m minus 1 all divided by 12, because it would get 6m minus 2m is 4m minus 1 over 12. Yeah. Finally, therefore, now we can calculate the area f of mn, which is just f of m plus 1 in this particular example. This is equal to the difference, which is the absolute value of the differences over 12 minus 4m minus 1 over 12, which is simply equal to m minus 1 over 6. But this is an exact number. And so m can be any even integer. M is any even integer, right? In that case, we can pick m arbitrarily big. So therefore, it is impossible to bound f of mn from above by c. So there's no such c which will bound this, because it goes in, it can be arbitrarily large, and that solves the problem. So this was a very I don't know, laborious exercise. Not that it's hard or anything, but it requires a lot of careful calculations and so on. That's all. But hope you enjoyed it, and looking forward to see you guys in our next video.